our final speaker for today, Mr. Haopeng Wang, and he'll be talking about absolute sets of rigid local systems. Please take it away.
Okay, thank you. I'm very happy to speak here. Today I will talk about absolute sets or rigid local systems. And this is a joint work with Nero Boudou and Leonardo Lorey. I will start with recall what is a local system. So today, let X be a smooth, complex algebraic variety. And then we define local system to be a locally constant shift on the underlying complex manifold. So the shift here is defined using the complex topology. And we only consider local systems with fiber or finite dimensional complex vector space. And the rank of a local system will be the dimension of the fiber. For example, the constant shift is a local system, and here we also call this rank 1 trivial local system. And another example of local systems is called geometry local systems, which are the higher derived direct image via a smooth and the proper morphism of complex varieties. And the origin of the project is the question here to classify the geometry local systems. And we want to classify these local systems in the module space of rank R, simple local systems. We call this Betty module space here. And the rank 1 geometry local systems are just the absolute Q bar points in the rank 1 in the Betty module space of rank 1 local systems. And this is a recent result by Nero Boudou and Haopeng Wang. And they also studied the positive dimensional analog of absolute Q bar points. And these are absolute Q bar constructible subset or absolute Q bar closed subset in the Betty module space of rank R, and R could be any integer. And today I will say something about the higher rank local systems, mainly about the absolute set. And if the rank is larger than 1, then Nero Boudou and Haopeng Wang conject that the point in the Betty module space here represented by a geometry local system if and only if it is absolute Q bar point. And this conjecture is very complicated in general. And to completely solve the conjecture is a very complicated question. So sometimes we consider some special local system, and which are called rigid local systems. To define the rigid local system, we need to fix smooth compactification for the X. And we assume the boundary divisor here is a normal crossing divisor. Then we define a simple local system. Simpleness here means irreducible, so there is no non-trivial sublocal system. A simple local system on X is called cohomologically rigid if the first hypercohomology group is vanishing. And here we firstly take the local system of traceless endomorphism of L. So it's still a local system. And then we take the intermediate extension functor via the compactification here. And then if the first cohomology group here is vanishing, then the local system is called cohomologically rigid. And this condition means that there is no non-trivial infinitesimal deformation of L. Simpson conjectured that any cohomologically rigid local system whose monodromy at the infinity has a torsion eigenvalue and the determinant is torsion is geometric. Today, I will introduce the notion of absolute set and discuss some conjecture by Nero-Boudou and Haopeng Wang. Then I will talk about the connection between these two conjectures about a geometry local system. So let me recall what is the Betti module space. So for a local system on X, and we assume the rank is R. R is a positive integer. And then we have a monodromy representation. So this is, we fix a base point on X, and then we take the representation of the fundamental group here to the automorphism group of the fiber. So this it gives a one-to-one correspondence between the category between the local systems and the monodromy representations. So actually they are the same thing. Then we take the variety, which is defined by this functor. So it's a representable functor, and then this is a farm variety. And we also have a GR action on the RB, the variety, the representation variety, RB by conjugations. And then we take the JIT quotient to be the Betti module space. And this is a cross module space of local system. So the point here uniquely correspond to simple local system. And this Betti module, this quotient is again a fine variety and is defined by the spectrum of the ring of invariant global section here. Okay, so we will study absolute sets inside this module space. And to define the absolute set, we also need the Riemann-Hilbert correspondence. So we need okay, I already mentioned this, and we also need another notion. So that is logarithmic connections, and this is a pair consists of torsion-free module, torsion-free sheaf of OX coherent module of rank R, and then a flat connection to the sheaf of logarithmic one forms. And the flat connection means a C-linear map satisfying the Leibniz rules, and the connection satisfy the condition here. Lambda 1 means we can extend the lambda here, the map, to the logarithmic two forms, and then the computation here is 0. So that's this condition is the flatness, and this condition is the definition for connection. So that's a definition for logarithmic connection. And then Neutral and Simpson prove that there exists a cross-module space of P semi-stable logarithmic connection of rank R. Here, the P here means the Hilbert polynomial of the sheaf, the underlying sheaf. So the semi-stability here defined by using Hilbert polynomial instead of the slope, normalized Hilbert polynomial. And the close point in this cross-module space corresponds uniquely to a class of semi-stable logarithmic connection of rank R. And the two connections are in the same class if and only if their associate drawdown holder filtration are the same. And further, neutral Saba Simpson proved that the Riemann-Hilbert correspondence into a analytic morphism between the associated analytic space of the two cross-module space we just defined. And the Riemann-Hilbert correspondence is the equivalence between the category of flat connections and the category of local systems. So the map here is we start with from a connection, a logarithmic connection, and then we take the restriction on X. Then this gives us a flat connection on X. Then we, by the Riemann-Hilbert correspondence, we have a simple local system. And this local system is by definition the kernel of the flat connection on X. And this is a analytic map. So this even these two module space are algebraic. I forgot to say the course module space here is a quasi projective separated complex scheme. So even these two module space are algebraic schemes, but the map here is an analytic map. Then now we can define an absolute set. So we will consider automorphism of the field of complex numbers, and then we take the base change via the automorphism here, and then we pull back the logarithmic connections. Will give us a map between the module space here and the module space of logarithmic connections on the dual variety. And note that this map is just a map, is no longer a geometry morphism or anything. And then for a field K to be Q or Q bar or C, then we defined K constructible subsets of the Betti model space to be absolute if firstly S inside the image of the Riemann-Hilbert map, and then if for any automorphism there exists K constructible subsets as sigma such that is preserved by the sigma action we defined before. And for absolute K closed subset, we define similarly. Sometimes we study absolute set inside absolute K constructible subset. And that's just by definition is the intersection with intersection OM with another absolute set. Okay. So we give some remarks about what we just defined. Firstly, the RH morphism, the map is selective if for rank 1 case or if the base variety is a curve. And if we defined MB upper S to be the subset of simple local systems, then firstly, this subset is risk open in the whole module space. And we know that this subset lies inside the image of RH. So what we just defined is meaningful. And the definition of absolute set is independent of the choice of compactification. This is because of the work of Nerbudu and Haopeng. They gave equivalent categorical definition of absolute sets. Which doesn't involve the compactification. So the definition of absolute sets is independent of choice of compactification. And now we give some example for the absolute set. Firstly, the the subset of simple local system rank R is an absolute Q constructible subset. And the second example are cohomology jump loci. So we define this by the dimension of the cohomology of this tensor product of local systems jump at k here. I mean the dimension jump at k is absolute Q-bar constructible subset when F here is a geometry local system. And actually, for almost all subsets inside the Betty model space defined by using natural functors and take the dimension of cohomologies are all absolute by the work of Boudou and Wang. The last example is the cohomologically rigid local systems. So that's the subset of all cohomologically rigid local system. And then this subset is absolute Q-bar constructible subset. And the result we have is about absolute subset inside MB rigid and inside MB simple. Okay. Near Boudou and bottom one have a package conjecture of absolute sets. So firstly, if S okay, let me introduce the conjecture here. So for S to be a absolute Q-bar constructible subset, then the conjecture says that its closure and the complement and the A-ray irreducible components are absolute again. So basically what said here. And the second property, conjectured property, is that point is an absolute Q-bar point if and only if it's a local system of geometry origin. So that is a geometry local system we just defined. And the last two property they conjectured is that the absolute Q-bar close point, so that the Q-bar points are dense inside the absolute set. And the conjecture 2, 3, and 4 together implies that the subset of geometry local systems is dense inside the Betty model space. And since this is a complicated conjecture, and sometimes we consider the conjecture inside absolute Q-bar constructible subset M, as mentioned here. And for rank 1 situation, Nero, Boudou, and Boudou Wang, they prove that the whole conjecture holds for any smooth complex variety for rank 1 local systems. And they actually prove a stronger result that the absolute Q-bar closed subsets are torsion translated of one subtory of the Betty model space here. And because in rank 1 case, the module space here is algebraic torus. So this makes sense. And for higher rank, so if X, the best variety, is a abelian variety or an affine torus, then the whole conjecture holds. And if X is projective, then the first property, so that is conjecture A1 holds. So now is my result with together with Nero, Boudou, and Larrey. So the firstly, for the subset MB simple, so that's the subset of simple local system rank R, the conjecture A1 holds. So that means the absolute Q-bar constructible subsets lies inside MB rigid, then it is generated from the absolute Q bar closed subset by a finite sequence of taking irreducible components, intersections, finite unions, and complements. And we also prove that the closure of absolute Q bar constructible set is again absolute. So that means it's absolute Q bar closed. And then the second part of the results says that if for MB rigid, so here is the absolute set of cohomologically rigid local systems, then conjecture A1, A3, and A4 hold, and the conjecture A2. So here I recorded this part is about the geometry local system equal to the Simpson conjecture. What we already mentioned in the beginning. So any cohomologically rigid simple local systems with some extra condition is geometry. So that means any point that's represented by local systems satisfy this condition is actually an absolute Q bar point. And since Simpson conjecture has been studied by a lot of people, and we already know these two situations. So if rank 2 or if the base variety X is dimension 1, and for any rank, the whole conjecture holds. That's basically because the Simpson conjecture holds. And now, instead of giving the proof, I will give an example. So if X is a curve, then the only non-trivial local system exists for X to be an open subvariety of P1. And in this case, we know that the MB rigid of rank 2 local systems on X is a finite disjoint union with the components are all isomorphic to a locally closed subvariety of the product here. And the C star up to the rank 2, sorry, this is a typo. So the here is denoted by the symmetric power of C star to 2. So the MB rigid of rank 2 local systems are a finite disjoint union of locally closed subvariety here. Okay, I will stop here, and thank you for your attention.
Okay. Thank you very